Hi, I'm Max Krempel and I'm with Anna Fasoli from Andor, and today is 19th of April of 2023, and Anna is doing a walkthrough and a training of new users for the Dragonfly, and specifically how to use it and what to do not to break the expensive instrument. Please start.
Thank you. Okay, so this is the Andor Dragonfly. It's a spinning disc confocal, and first of all I'll show you how to turn it on. So there are 3 power strips here on the left. Let's start with those. They're numbered 1, 2, 3, and there is also a 4th one down there that has a switch over here. The computer in this case was already on, but in case it's not on, you can also turn on the computer.
Where is the
after.
computer switch?
It's here with the green label. Okay, everything is now turning on. The Windows will have different users. If you don't have one, you will create a local user account. Maybe I can show you later how to do that. In this core facility, we have a Windows account for every lab. So each lab will have its own settings and its own way to run the software. Today, I'm going to use Andor's account. Okay. The software that it's running the Dragonfly, it's called Fusion. And I just double click to turn it on. Okay, that's Fusion. And while the software is turning on, I give you a quick overview of the system, of the hardware. So we have 2 cameras on. The smaller camera is called the Xyla, and it's an SCMOS. And this is the Ixon, which is an EMCCD. This camera is probably the most used camera. It has a smaller pixel size, so you will have a higher resolution in your image. And it's a 4 megapixel camera, so your image will be a 2048 by 2048 always. This is the EMCCD, which is a most sensitive camera, so it is very useful if your sample is very dim, or for example if you're doing custom imaging, you're trying to go fast, or you don't want to use a lot of laser power. This will be able to pick up much more light compared to the Xyla. However, there is a downside, which is that the pixel size is bigger, so your resolution is not going to be as good as Xyla. So image quality is a bit less, but you can see much more light with this one. So you have to choose depending on what experiments you want to do, and you can just try different cameras to see how your image looks like to decide which one to use for your experiment. Once your sample is centered on top of the objective, we want to focus on it, right? So the quickest way to focus is to look through the eyepieces of the microscope.
Can you damage your eyes? Can laser hit your eyes?
No.
Okay.
In this case, we're going to use only LEDs to look through the eyepieces. If by any chance the laser is on, anytime you put your microscope so that the light will go out from the eyepieces, the laser shuts off automatically. This is called a laser safety interlock system that knows when something is in a position that can send light toward your eyes, the lasers will automatically shut off.
Okay.
And there's going to be also a warning on the software telling you that the lasers are not able to turn on because there is something in the light path that can send the laser toward your eyes.
Is it electronic safety or mechanical?
It's a mechanical, it's a magnet.
Okay.
So if you can, for example, if I want to tilt the arm of the microscope, right? You can open here and I can tilt it.
Oh, really?
Can you hear the magnet?
Yeah, there is some click.
The click, that's the magnet. So because you can potentially look down and get the laser in your eyes.
Okay.
So that's why tilting this arm will open the circuit and prevent the lasers from firing. Another thing that will prevent the lasers...
Just a second. So the users wouldn't do that, right? They don't have no reason to do that.
To do this?
Yeah.
Sometimes...
Only for service, right?
No, sometimes user will have to do it if they want to work more on their sample. You want to have more space. Sometimes I like to do
Like
this
if there
myself.
is a bigger sample, like
Yeah, if you have something
if there is
big.
a mouse.
Yeah, or even if, I don't know, maybe they're doing some, if you have the incubation chamber and you want to be able to lift the lid, or maybe if you want to pipe it in something.
Okay, for piping, got it.
Yeah, yeah. So that's something that, yeah, so you just have to slide these two doors and tilt the arm.
Okay.
Okay, let me bring it back.
Okay.
Like that. Okay, now, yeah, so we want to focus on the sample. So the sample is on top of the objective and I want to turn on the light. So first of all, I will turn off the light for the chamber because I don't need that light. So I'm going to use the foot switch like that. And there are two ways to look at your sample with the eyes. One way is to use transmitted white light.
Okay.
So we call it bright field. The light is coming from the top and it's transmitted because it transmits through the sample and goes to the objective and toward your eyes. To turn on that white light in the back, we use this controller. WHT means white, so you know that that's the white light from the back. You just turn it on and you see that the light has turned on from here. So if I put my hand, that's the light coming.
The light,
yeah, that's the light coming from the top.
Can you open this?
Of course. Yeah, we're not using an incubation, so.
Can you turn it off?
Yep.
Okay.
Yeah.
Thank you.
If for some reason you don't see the light coming from there, it could be that the intensity is too low.
Okay.
I believe under a certain percentage.
It's weaker. And
It's going to be weak, so after 0.6 it's probably going to turn off. So check that the intensity is, around 4 or 5%. That should be enough. Another thing that you want to check is this lever over here, the stop. That is a physical shutter that can prevent the light from going down. So this, you can see if I change it, the light goes on and off.
Let me see. Okay, got it.
Okay, so that could be the second reason why you don't see light coming from the top. Yeah. Okay, so I have it on now. I want to look through the eyepieces. In order to send the light to the eyepieces, I will go here in the panel where you select the objectives. If you click on the eye, then the light will come to the eyepieces. So I don't know if you can see it.
No, the camera sees not just something, but
You see
nothing
light, yeah.
photos.
So now it's not,
Okay.
and now it's
That's
there.
something changed.
Yeah.
All right.
So I just look down through the eyepieces and I see some shadow. It's not in focus yet, but slowly, okay, now it's in focus.
Oh, so you manually adjust.
I manually moved the microscope knobs,
Okay.
so I changed the Z position,
Okay.
the height of the objective until the sample is in focus.
Okay.
If,
Can you break the glass? Can you break the microscope?
yeah, if you go too high, you can touch the slide and push it.
Okay.
So always, if you are having trouble focusing, always go back to your sample and make sure that the slide, the objective is not touching the slide.
So on 10x, the glass doesn't stick out, so the metal would break the slide. Not the glass would be fine, right? lens of
Oh,
the-
I see what you mean. It depends. You can still, if the glass breaks, it can still scratch the lens. So
All right.
yeah.
So if you cannot find the focus, what do you do? Is there a
Call
way to
Max.
go a lot up? How do you know if you're close to the slide if you don't see it? How would you know?
Well, you will see. So if you're having trouble, what I recommend, okay, is to not use the metal brackets,
Okay, okay.
okay, and keep like those. I'm gonna lift them up now because these are made so that your sample does not move. So you can move them on the side,
Okay, okay,
so
okay.
they don't push down the sample, and leave it. So I will make this space a little bit larger, so my
Yes,
slide has moved to kind of go up and down.
That's what I wanted to
So
show
if
you.
I now go up, I see that you can physically see the
So
slide
it's
that
safe
is
to do
rising.
that for 10x.
For all the objectives.
All objectives would
Yes.
survive that?
Yes.
Okay.
Yeah.
So for all
Not
objectives,
recommended
we
though.
can
This is just for very inexperienced users that don't know how to
For the
focus.
very inexperienced user who cannot find the focus, that's what you would do.
Start with a loose sample that even if the objective pushes it a little bit, you're not gonna break it.
Excellent. But the experienced user would just go from bottom to top and would find the focus.
Yes.
And if they don't find, they hear the crack. If they miss the focal length, right? Focal position.
Right. I mean, you can see that. Just keep an eye on the objective always. If it's too close, go back down and start again.
But you don't know if it's too close or too far, right?
An experienced user will know.
Okay. All right.
Yeah. And this is just one way to find your focus. The other way that you can use if, for example, your sample is too thin and too transparent, like a single layer of cells, it's kind of hard to see. You just see some shadowing, but not that much. So if your sample is fluorescent, we can check through the eyepiece with fluorescence.
Okay.
It's not going to use the lasers, we're going to use an LED. And the light is coming not from the Dragonfly, but from the back of the microscope. So, not from the top, but from the back. There is a port in the back.
And where are the LEDs located?
So the LED box physically is this one here. And we have a liquid light guide
Okay.
that plugs in the back of the microscope. So the light will enter from the back of the microscope, will be reflected up to the sample from the objective, and then goes back down and to our eyes.
Okay.
In order to turn on the colored LEDs, there's going to be the second controller here. A big button says on off, so you can turn it on. Okay, and you see we have 3 bars. These are the 3 different colors: UV, blue, and green. when the bars are full like that, it means that all the three colors are on. And that's okay. We can have the three colors on at the same time because we control the wavelength of light coming from the objective by choosing the filter cube underneath the objective. To choose the filter cube on the touch screen of the microscope, we click here, and you see we have different options in terms of filter cubes. Dragonfly is an empty position, and that's what you would normally have when you're imaging in confocal mode with the Dragonfly, or you're looking at the bright field light. So it's not going to filter any light because there is no filters in place. And then we have DAPI, FITSI, and rhodamine. DAPI is for the UV channel. So if I click DAPI, I don't know if you can tell, but there is a bluish
I think it can see.
UV light coming from the objective.
Yep.
If I click, and so that will allow you to see the UV 405 channel, right? So the DAPI, if you have it on your sample, Hertz, or any DNA stain. FITSI will allow a wavelength around 488 to come from the objective, and so you will see emission in the green. So anything that is a 488 or a GFP, you will see green from the eyepieces. Rhodamine is green light, and this is for the red channel. So anything that is RFP or side 3, that you will be able to see with this third filter cube. Okay?
Can you repeat the colors? No, just for rhodamine.
Rhodamine is RFP or side 3, anything that is around red wavelength. So I would say 560 nanometer. Okay, so that's another way to check for your sample, and you can again see fluorescence if you look here through the eyepieces. Once you're done and your sample is in focus,
And the last button here.
the last one is for the micropoint. That's for an advanced training, maybe tomorrow.
Can you explain what it is?
So micropoint is a photostimulation device that it's also plugged in the back, that is used for wounding or ablation.
Right.
And it has a specific wavelength. So when we want to use micropoint, we use a filter cube that reflects. It doesn't have any excitation and emission filter. It only has the dichroic to reflect the wavelength from the micropoint, which is 435 nanometer. And then everything else can be imaged with the Dragonfly.
What's the abbreviation for ablation?
Ablation?
There is some 3-letter abbreviation for that method. When you kill the fluorescence in half of the cell and then it diffuses.
Oh, that's FRAP.
FRAP is not the same thing?
It's not the same. Ablation is more like, you can also do FRAP with micropoint, but it's not very efficient. Ablation is actually physically cutting tissue.
Okay.
Like if you want to cut a neuron or I don't know, like remove just one cell from the tissue and see how the tissue recovers after the wound.
Okay. And it's safe for the eyes? Do you need to wear glasses or something?
No, you don't. And since this is a laser, it will always be interlocked. So if the microscope is in the eye position, you are not able to use the micropoint laser.
Okay.
Everything is laser safe.
But basically don't touch MP.
Yeah, it's useless unless you're using the micropoint. Yeah.
Okay.
And so once you're focused, it doesn't matter what type of light, always remember to turn it off from the control pads, because the software doesn't control these light sources. So we have to remember to turn it off.
So here it says off, and here the bars become
Striped instead of being full. So, and it will say off here as well.
Okay. Got it.
Okay. You don't have to remember to bring back the filter cube to Dragonfly, because that can be controlled from the software. So then when we move to the software and we start using the Dragonfly, the microscope knows that it has to go back to Dragonfly by itself.
Okay.
So that's something that you don't have to remember. But the light, yes, you have to remember.
So what's the logic? Why is it called Dragonfly?
It's because we use the Dragonfly.
So this one is a source, basically it's a lasers, and the other ones are not lasers?
Exactly. So when we use the Dragonfly, there is actually no filter cube. It's going to be an empty position underneath the objective. And that allows us to use all the lasers coming from the Dragonfly.
And where are the lasers located?
Oh, the lasers are down there.
All right.
Two boxes.
So the big ones?
Yeah, the big ones, yes.
And this small one is what?
That's the Borealis unit. It's a homogenizer for the multimode fiber of the laser.
Homogenizer meaning making it uniform?
Yeah, making a uniform illumination. Yes.
Okay.
And yeah, the laser entered the Dragonfly in the back, there. That's
All right.
yeah.
Which one? Oh, that little
The metal one.
metal,
Yeah. Yes, that one.
how do you call it?
A fiber.
Cable,
Yeah,
fiber cable.
Yep. So they enter there, they go in the microscope to the sample and that back into the cameras.
To the cameras, yeah. So from the laser to microscope to the cameras.
Yep.
To the cameras, to these ones, okay?
Yeah.
To these ones, yeah, both. Pose here.
Okay, now that the sample is in focus, we can move to the software and start doing some imaging with the confocal part with the Dragonfly.
Pose here.
Okay. The first thing that you want to do on the software before starting any imaging is to make sure that you're saving in the right folder. So to get to the File Manager folder, you can click the three dots over here that says Navigate to the File Manager, or you can also go to Imaging, Preferences, and find the File Manager tab here. So at the top, you can browse and select your own folder. Remember to always save on the D drive. And also when you're finished, remember to copy all your data to your external hard drive, because data on this computer might be deleted regularly to keep the hard drive available for everyone. So I'm going to currently save in the folder called Endor. And as you can see inside, there are subfolders which have the date in which they were created. These folders are created automatically. So if I just select the Endor folder, click OK, you can see here it says subfolder creation daily. This means that every time you start some imaging and you save something in that folder, automatically Fusion will create a subfolder with that date. Another thing that you can select in this page is how your file name will look like. So, for example, in this case, we have this, you can see here the example file name. It will start with the image name that you can put it in Fusion. I'll show you later where. And then you can decide what else to print in the file name after that image name. It could be the date. You can also add the time. You can also add protocols or channels if you want to, but I find that that will make the file name really long, so I usually don't use them. So I like to have date and time. And you can also choose the order of these things. So if you want your file name to always start with the date, you can select date and move it up. So now you see your example file name will be the date, your sample name that we put it in the imaging part in Fusion, and then the time. So if I go back to imaging, this is where you put in the image name. And since in Fusion everything is automatically saved every time you do an acquisition or you take a snap, you want to insert your image name before starting the acquisition, before starting the experiment. So in this case, I will just put in training. So again, my file name will look like today's date, training, and the time. Or if I want, it could be training, today's date, and the time. But I like to have the date first. Okay, so back to imaging. This is just an old image, and usually Fusion will show up at startup the last image that was taken. But I know that my sample is in focus right now, and I can start with going live and selecting the wavelengths and the channels that I need to do my imaging. But first of all, I want to give you an overview of the Fusion software. So this big panel on the left side is what we call the image panel, the image display panel. Sometimes when you open Fusion, you might see it in this version here, which has a larger area for the image and just this light gray area that we call the remote, because it looks a little bit like a TV remote. To expand and see more details, you have to click on this arrow here on the side to expand the right tab. Okay, so to visualize the image, we have different ways to do that, and you can see that here on the left side. Currently, this is just a 2D image, but let me go and select a 3D image so I show you how many ways to visualize an image. So I go to the file manager, and this is just a list of images that have been taken previously. So I can open an old image, say this one. Okay, so I know that this is a Z stack because I see from the bottom that I have the Z scroll bar. So if I click on the white bar here, and I can scroll and check my Z stack. That's because we're in the 2D mode. If I do MIP, so the second one is going to be the maximum intensity projection. This is a bit blown up. I will explain later what I'm doing here. Okay. The third one is a 2D, but it will be split in different channels. So we have again the Z bar that you can scroll at the bottom. And here you can see channel number 1, channel number 2, and the overlay. All right, so from the list of channels, I will start by selecting the confocal CF40. And you can see here that in the list below, we have some of the channels, not all of them, because 3 are already in the protocol from CF40. So you will notice that for each of the lasers, in this system, you have 405, 445, 48, 561, 637, and 730. You have 2, I'm going to remove them here so we'll see them all in the same list. We have 2 channels for the same laser. And that's because we have, for example, 405 for the Exxon, the EMCCD camera, and the 405 for the Xyla. That means that depending on the camera that we want to use for our experiment, we have to select that specific channel. So that the microscope will change the mirrors and send the light to that specific camera. Usually, we use the same camera for all the channels, and we will collect all the channels sequentially. So you can collect first, for example, the 488, and then the 561, and then the 637, always with the same camera. So in this case, I will click 488 for the Xyla, and you see this is a confocal. And when I click, I think I left my microscope toward eyepieces, and maybe there was already a filter cube, but the software will bring everything to the right position. So I click this channel, and now this becomes my active channel over here. And this is just, so if I go live, I should be able to see something. Now, you can see that there is almost nothing on the screen. And that could be because my sample is maybe not perfectly in focus. Sometimes it's focused through the eyepieces, but when we focus on the camera is a little bit different. And the second thing that might happen is that maybe our display settings are not correct. Maybe we're just not displaying the right pixels intensities on the screen, as I explained later. So the first thing that you want to do is actually click Auto. Automatically scale the pixel intensities on the image. So when you click Auto, the software automatically changes these values over here so that I can have a little bit more contrast. Because say maybe before it was around 700, you see everything is dark. If I click Auto, brings it back to 183 so I can see more values. And I can see some structures in the back, so I'm going to try to focus a little bit. You can focus using the knob of the microscope or by clicking here up and down in the software. And I can see more structure showing up here. So I want more contrast. There you go. So I have something here. And now say that I want to check another channel. I can reopen my list of channels, click on the 561, same camera. So for the Xyla, I can click on it. And there you go. I have my signal from the 561 channel. And same thing for the 637 channel. It's there. Okay, I can put this back to 10%. All right. So once I know what colors my sample have, I can add them to the protocol. To add them to the protocol, you can just click plus over here. So I will add the 488, the 561, and the 637. So those are currently in the protocol over here, and they will show up in the list above. I will also stop live because I don't want to bleach my sample. If you stop live, the last image collected will show here. If you want to have a reference of what you're doing, you can click Snap, and Snap will just take a single frame with whatever active channel is at the moment. Okay, so let's go down here and go over the sample navigation. I've already put in my image name, and there are a few things that we can do to get an overview of the sample. So I'm going to go live again with the 561 channel because it's the brightest one. So to change channel, you can go back to the list here and click on the 561, or you can also directly click on the channels that are in the protocol. Okay, so I will go to 561 and go live. And I can move with the stage to navigate and find my sample and move up and down using the software here or the microscope knob. But a quick way that I can use to do an overview of my sample is the 3x3 button. The 3x3 will automatically start a 3x3 montage of the sample, which is not stitched perfectly. It will just put the images, the tiles side by side to give you an overview of the sample. But it's a very quick way to get an overview, especially a low magnification. And since the stage is encoded, that means that every pixel on the image corresponds to a coordinate on the stage. And that is useful because then I can use this button over here that if I click it, it will turn on this white borders around the image. And I can select an area on the image, for example, this area over here, and click on the screen. And the stage will move to that location. So if I now go live, this will be in the center of the field of view. And there it is. While this button is active, I can also use it to navigate in live mode. So if I click here, for example, that will go in the center. If I click here, that will go in the center, and so on. These coordinates are saved also if you change objective, so you can take an overview of your sample at low resolution, say at 10x, and then as long as you haven't moved your sample on the stage, you can use the same coordinates to navigate at, say, 40x or 60x. Okay, so now that we have this overview, we have our channels. I wanted to talk about how to select the correct exposure time and laser power. So while being live, it's always good to open the histogram and check our values. A good measure of knowing how good your image is to calculate the signal to noise ratio. The signal to noise ratio is the difference, or the signal to background ratio is the difference between what values are in the background and what are the maximum values in the image. More or less, this corresponds to the min and max levels when you're doing the auto scale at the first level. I wouldn't do that if I'm at a higher contrast level, because then the maximum value is shrinked a little bit. So make sure that you're here, or make sure that your image looks nice. If you want to change this value manually, just make sure that you see that nothing is too saturated or too dim. So more or less like this. In this case, the minimum, the background is around, to make it easy, I say it's around 100, and the maximum is around 2000. So my signal to noise ratio is quite high in this case. It's 20, and that's a very good signal to noise ratio. Usually for live samples, a signal to noise or a signal to background ratio of 2 or even 3 is good enough. That's because you don't want to blast your cells with too much laser, and maybe you also want to drop your exposure time to image fast, so the camera doesn't have enough time to collect a lot of signal. And I'm going to try that. I'm going to put the laser to 2% and the exposure time at 20. And you can see that now I don't see anything because my pixels are very dim. So if I auto scale again, and I can leave that on, you see this is some very dim signal, and this is a signal to noise of 2 exactly. But you know, for some experiments that is enough, because if you use more lasers, maybe you bleach, or you have to go that fast and you want to keep your cells alive for a longer time, so you want to have your laser low, this could be enough. So usually if you want to take a very pretty image, a signal to noise of 10, so you're having your maximum or around 1000, it is very good. It will give you a very nice contrast image, but it doesn't have to be that way. It really depends on what you're trying to do with the sample, how long you want to image for, how stable is the fluorophore, etc. So I go back to say 5% and 100 millisecond and auto. Now this is 5, very good. 5 signal to noise, I mean. 10%, that should be around 10. Yes. So this is a very good image, very good contrast, but don't feel like you have to have this level of intensity for everything you're doing. This is a very bright sample that I'm using for training, and it's probably not comparable to live tissues or cells. All right, so from the list of channels, I will start by selecting the confocal CF40. And you can see here that in the list below, we have some of the channels, not all of them, because 3 are already in the protocol from CF40. So you will notice that for each of the lasers in this system, you have 405, 445, 48, 561, 637, and 730. You have 2, I'm gonna remove them here so we'll see them all in the same list. We have 2 channels for the same laser, and that's because we have, for example, 405 for the Exxon, the EMCCD camera, and the 405 for the Xyla. That means that depending on the camera that we want to use for our experiment, we have to select that specific channel, so that the microscope will change the mirrors and send the light to that specific camera. Usually we use the same camera for all the channels, and we will collect all the channels sequentially. So you can collect first, for example, the 488, and then the 561, and then the 637, always with the same camera. So in this case, I will click 488 for the Xyla, and you see this is a confocal. And when I click, I think I left my microscope toward eyepieces, and maybe there was already a filter cube, but the software will bring everything to the right position. So I click this channel, and now this becomes my active channel over here. And oh, this is just, so if I go live, I should be able to see something. Now, you can see that there is almost nothing on the screen. And that could be because my sample is maybe not perfectly in focus. Sometimes it's focused through the eyepieces, but when we focus on the camera it's a little bit different. And the second thing that might happen is that maybe our display settings are not correct. Maybe we're just not displaying the right pixels intensities on the screen, as I explained later. So the first thing that you want to do is actually click Auto. Automatically scale the pixel intensities on the image. So when you click Auto, the software automatically changes these values over here so that I can have a little bit more contrast. Because say maybe before it was around 700, you see everything is dark. If I click Auto, brings it back to 183 so I can see more values. And I can see some structures in the back, so I'm going to try to focus a little bit. You can focus using the knob of the microscope or by clicking here up and down in the software. And I can see more structure showing up here. So I want more contrast. There you go. So I have something here. And now say that I want to check another channel. I can reopen my list of channels, click on the 561, same camera. So for the Xyla, I can click on it, and there you go. I have my signal from the 561 channel. And same thing for the 637 channel. It's there. Okay, I can put this back to 10%. All right. So once I know what colors my sample have, I can add them to the protocol. To add them to the protocol, you can just click plus over here. So I will add the 488, the 561, and the 637. So those are currently in the protocol over here, and they will show up in the list above. I will also stop live because I don't want to bleach my sample. If you stop live, the last image collected will show here. If you want to have a reference of what you're doing, you can click Snap, and Snap will just take a single frame with whatever active channel is at the moment. Okay, so let's go down here and go over the sample navigation. I've already put in my image name, and there are a few things that we can do to get an overview of the sample. So I'm going to go live again with the 561 channel because it's the brightest one. So to change channel, you can go back to the list here and click on the 561, or you can also directly click on the channels that are in the protocol. Okay, so I will go to 561 and go live. And I can move with the stage to navigate and find my sample, and move up and down using the software here or the microscope knob. But a quick way that I can use to do an overview of my sample is the 3x3 button. The 3x3 will automatically start a 3x3 montage of the sample, which is not stitched perfectly. It will just put the images, the tiles side by side to give you an overview of the sample. But it's a very quick way to get an overview, especially a low magnification. And since the stage is encoded, that means that every pixel on the image corresponds to a coordinate on the stage. And that is useful because then I can use this button over here that if I click it, it will turn on this white borders around the image. And I can select an area on the image, for example, this area over here, and click on the screen, and the stage will move to that location. So if I now go live, this will be in the center of the field of view. And there it is. While this button is active, I can also use it to navigate in live mode. So if I click here, for example, that will go in the center. If I click here, that will go in the center, and so on. These coordinates are saved also if you change objective. So you can take an overview of your sample at low resolution, say at 10x, and then as long as you haven't moved your sample on the stage, you can use the same coordinates to navigate at, say, 40x or 60x. Okay, so now that we have this overview, we have our channels. I wanted to talk about how to select the correct exposure time and laser power. So while being live, it's always good to open the histogram and check our values. A good measure of knowing how good your image is to calculate the signal to noise ratio. The signal to noise ratio is the difference, or the signal to background ratio is the difference between what values are in the background and what are the maximum values in the image. More or less, this corresponds to the min and max levels when you're doing the auto scale at the first level. I wouldn't do that if I'm at a higher contrast level, because then the maximum value is shrinked a little bit. So make sure that you're here, or make sure that your image looks nice. If you want to change this value manually, just make sure that you see that nothing is too saturated or too dim. So more or less like this. In this case, the minimum, the background is around, to make it easy, I say it's around 100, and the maximum is around 2000. So my signal to noise ratio is quite high in this case. It's 20, and that's a very good signal to noise ratio. Usually for live samples, a signal to noise or a signal to background ratio of 2 or even 3 is good enough. That's because you don't want to blast your cells with too much laser, and maybe you also want to drop your exposure time to image fast. So the camera doesn't have enough time to collect a lot of signal. And I'm going to try that. I'm going to put the laser to 2% and the exposure time at 20. And you can see that now I don't see anything because my pixels are very dim. So if I auto scale again, and I can leave that on, you see this is some very dim signal, and this is a signal to noise of 2 exactly. But you know, for some experiments, that is enough, because if you use more lasers, maybe you bleach, or you have to go that fast and you want to keep your cells alive for a longer time, so you want to have your laser low. This could be enough. So usually if you want to take a very pretty image, a signal to noise of 10, so you're having your maximum or around 1000, it is very good. It will give you a very nice contrast image, but it doesn't have to be that way. It really depends on what you're trying to do with the sample, how long you want to image for, how stable is the fluorophore, etc. So I go back to say 5% and 100 millisecond and auto. Now this is 5, very good. 5 signal to noise, I mean. 10%, that should be around 10. Yes. So this is a very good image, very good contrast, but don't feel like you have to have this level of intensity for everything you're doing. This is a very bright sample that I'm using for training, and it's probably not comparable to live tissues or cells. Okay, so each channel has some settings that you should never touch, because as I said, all the channels are already pre-made and they shouldn't be modified. But if you go into the first tab, which is the channel manager, you can actually see how the channel is created. So for each of these channels, you see that we have the light source, that in this case, since it's a 561 channel for the Silas CF40, we have the 561 nanometer laser on, and we are using the first dichroic because the first dichroic has the 561 in the list, so meaning that it's letting the 561 passing. Then from here, we're not doing any triggering of the bright field light because this is a laser. We're using the laser. We don't need the bright field light. And then from here, we go to the filter wheel. So the filter wheel, in this case, we have to look at the top one. You see this arrow is pointing up. The top one means that it's the filter wheel for the Xyla, which is the camera that we're using. And this is the emission filter currently in place, which is the 594-43. So we're collecting the light around yellow-red wavelengths. So this is the basic channel setting. And here at the bottom, we see the global settings. The global settings tell us what are the current status of the microscope, the camera, and also some things of the confocal units. So the microscope is currently on a 10x objective, which is the one that I selected from the display, the touch screen on the scope. Be careful that if you click here, it will change the objective automatically. So you want to change objective only when the objective is lowered down at its lowest position. If you expand here the objective information, you can see the current information of the objective. And also if you stop without clicking on the objective, you can see their magnification and the NA. Currently, you still don't have the 40x water, but you can see here the difference between the 40x glycerol and the 40x water. The 40x glycerol has a higher Na of 1.25, while the water is 1.1. Here we have information about the camera. Currently, the Xyla is acquiring in high quality mode. The other mode will be high speed. If you really need to go as fast as possible, you will have to. So if your exposure time is, say, lower than 10 milliseconds, you're doing calcium imaging high speed, you want to put the Xyla in high speed mode. The bit depth is standard 16-bit, but you can also do 12-bit again to try to go faster, but that will reduce your dynamic range. Other things that you can change, we usually never use frame averaging because the camera is already doing averaging and it's not going to increase the image that much unless you really want very nice contrast. But of course, it's like on a point scanner. If you do 2 or 4, it will take twice as much or 4 times as much. Then we have the option to crop the camera. Cropping the camera means that you don't use the whole chip of the camera, you don't use the whole 4 megapixels. You can use less of them. So you will reduce your area of imaging and reduce the number of pixels. We have some predefined areas here. Or alternatively, you can also, if I snap right now, this is still my 3x3 montage, but if I snap again, you can change the cropping manually by using the AOI tool over here. That will create this the square over here that you can modify manually and say, I want to image only this part of the sample, and you click enter to confirm your selection. So if I press enter right now and I go live, now you see that these values have changed. If I go live, this is what I'm seeing, only this area of the camera. To reset and go back to 24:8 by 24:8, you can either do it from the drop-down menu here in the global settings or from here resetting the area of interest. And we go back to full frame. Another thing that you can do is binning. Binning means that you group 4 pixels as if it was 1 when you're doing the binning 2 by 2. So it means that the Xyla, from being a 24:8 by 24:8, will become a camera, will become a 1024 by 1024 image. So if I can do binning here, you will see that the image got a little bit more grainier, so you have less resolution. Binning is something that you will have to do if you want to use 2 cameras at the same time, because as I said at the beginning, the EMCCD, the Exxon, is a 1024 by 1024. So to match exactly the pixel size and the number of pixels in both cameras, you will have to do binning of the Xyla. So I'm gonna go back to 1x. Another thing that you can control from the global settings is the camera magnification. Camera magnification helps if you want to zoom in the image, because we don't have a digital zoom like the point scanners. You can zoom in with a physical lens without changing the objective. So say that you want to zoom in a little bit more and you really like the 25x water, for example. You don't want to go to a 40x glycerol. You can zoom in by, again, I'm using the Xyla, so top arrow. You can zoom in and do 2x, and that will physically put an extra lens in front of the camera to zoom in your image. So your pixel size will be smaller. You're still imaging at 2048 by 2048, but your pixel size is smaller at the image, right? Because you're zooming in. I'm going to go back to 1x now. So again, never change the channel settings. This is something that is automatically created in Fusion, and you don't have to change because the channels are already pre-made. I'm now going to try, I don't think the sample will fluoresce, but I will just show you if I change to the let's try the 445 channel for the Xyla. Now it's changing, and this is the image. There is a little bit of fluorescence. You will see that in this case, the dichroic is the second one, because the second one actually has the 445 band pass, so it will allow you to see the 445. So, well, the first one only has the passing bands for the 405, 48, 561, 640, and 730. If you want to use the 445 in a protocol with other channels, you can see that in the same dichroic you will have the 561 and the 640. So it means that if you have an image with 445, 560, and 740, you don't have the 514 laser, you can do the same, you can do the imaging with the same dichroic. But for example, if you want to do 445 and 488 in the same protocol, you will have to wait for the dichroic to shift, because the two channels will have two different dichroics. So you have to allow for a few seconds for the dichroic to move. Okay, I'm going to go back to the 561 channel. All right, so once I'm happy with my channels and I have the right protocol, what I want to do right now is to change to a higher magnification objective. As I said before, I'm going to stop live. This is a snap that I just did, but I want to go back to my 3x3 overview that I just did. So I will open this image, just double click, and this is my 3x3 that I've taken with the 10x. And now I want to move, say, to a 63x to take a nice image. So the first thing you want to do is to drop the objective to its lowest position, not to damage the sample or the objective, which is most important probably. So we have two ways to do that. You can do it manually from the microscope stand using the knob, or in the software you can also do Escape Z. So it will escape the objective, meaning that it will go all the way down. Now from here, you can click to whatever objective you want to use. In my case, I want to go to the 63x. So I click 63x. The objective has moved. Now, since this is an oil objective, I want to add oil to it. One thing that I can do is to move the stage, and I'm going to pause here and turn on the camera to show you how I do it.
I've changed the objective from the software. You could have also done it from the display, but that's your preference. Remember always to drop the objective to its lowest position before changing it. Now I'm going to turn on the light in the incubator so that I can see what we're doing. I use the foot pedal here, and I grab the oil. Now remember that here you have...
Can you show the bottle?
Yes.
Close up.
Here you have two different types of oil. This is the oil for the 63x.
And what are you looking at? Type F?
This is the type F.
Okay.
And the refractive index is 1.51.
And what's refractive index? I know, but...
Well, the refractive index is basically tells you, I don't know exactly
how
how to
dense
explain.
it is. And
Yeah.
From water to the oil, it would change the angle of the
It
light.
will change the angle, but this is exactly the same. So the light, when it passes through glass and then to this oil, is not going to bend. And that's why
so same as glass.
It's the same as glass. So it's important, that's why it's important to have the cover slip that is 1.5, because the refractive index of the glass, that thickness is exactly 1.51, and a lot of mounting media for fixed cells have a refractive index that is very similar. So that means that when the light is coming out of the objective through the oil, through the cover slip in the sample, it will not bend, and so you have less diffraction, high contrast, and less aberrations.
Nice.
The other oil that we have is the type G immersion liquid, which is for the 40x 1.25 NA objective. The reason is that to have the glycerol is that its refractive index is 1.45, so it's a little bit less. 1.45 matches closely biological tissues. So if you have something that is thick, like an organoid, or a sample that is transparent, for example, and you want to image deeper, the 40x glycerol will better match the refractive index of the sample, so you have less diffraction when you're imaging thick tissues.
So where do you put it?
You know, on top of the objective.
So that's for water objectives and that's for oil
This is for the
objectives?
glycerol objective. The 40x 1.25 NA glycerol objective. This is the 63x 1.4 oil.
And is there like a water objective or?
There is also two water objectives. The 25x is water, and the 40x that will arrive is also water. So for those, yeah, water, the 25x water is also good for very thick tissues and live cells, and also the 40x water is good for live cells. Anything that it's on a petri dish in PBS or water, that really works. But also, you know, you have to choose. Sometimes people do live imaging with the 63x oil because they need to zoom in at 63x. So, of course, in an ideal world, you have all the objectives available. So you have to kind of work with that. So currently, I'm gonna use the 63x. Mine is a fixed sample, very thin, so I know that the 63x oil will perform very well. Okay, so just remember the type F is for the 63x oil, while the type G, the glycerol, is for the 40x 1.25 objective. Never mix them, so be careful when you use the two immersion oils. And also, if your sample has touched already the oil and you want to go back to a glycerol, you have to very carefully clean the cover slip before changing the objective, because we don't want to stain an oil objective with the glycerol.
Do you need also to clean the objective?
You will also have to clean the objective, yes, but that you can do at the end of your experiment.
Okay.
Okay, so now I've dropped my objective, and in order to put on the oil, what I'm going to do, an easy way to do it, 63x. An easy way to do it is to move the objective, so actually move the stage, so that I can reach the objective. So I'm moving with the stage, so I can reach the objective easily, like that. So I'm going to open the bottle and just put a little drop of oil, trying not to touch with the plastic the objective, not to damage it. So just let the drop go. And now I want to go back to exactly where I was before. So I'm going to use the tool that I showed before, which is the click and center in the software, to click on the screen and move the stage on top of my sample exactly where I wanted it to be. So if I click on the... So I know that my sample is going to go back into the same position because the stage, as I said, is encoded. So all the pixels correspond to coordinates of the stage. And now I'm going to go back to the Fusion software to refocus and start imaging in a protocol. Turn on the light.
I have just changed the objective to 63x and I've added the oil. by moving the stage, putting the drop, going back. As you can notice here, since I used Escape Z from the software to drop the objective down, I can now do refocus. So if I click refocus, the objective will go all the way up, and it's always good to check with your eyes. So making sure that actually the oil is there and it's touching the cover slip. In my case, I see that it's there. So I can go live again, and the objectives, the different objectives have similar focal points. So if I go live, I should be very close, as you can see, to the focus, and that's the case. So I can again adjust my focus here in the software a little bit, or if you want to be more precise and manual, you can also do it with the microscope knob like that. And again, I can stop live, and this is the 3x3 that I've taken before. I can use this to navigate to areas of interest. So I turn on this button, which I call the click and center, and I can, for example, go to this cluster of cells. If I click there, the stage will move in that area. And if I go live, that will be the area where I just clicked. Okay, so I'm going to turn off this click and center, and I will move to the protocol to set up a protocol and actually do an acquisition. So I click on this tab here, which is the protocol manager, and in the protocol manager you can create new protocols and save them. You can call them whatever you like. Each protocol can have same amount of channels. Usually we're going to use the same camera, and we have different types of protocols here that you can choose from. The most simple one is just a time series, so you're not going to take a Z stack. It's going to be just a time repeat. So yeah, time lapse. And the most common one is usually the Z stack, so it will allow you to take still a time lapse if you want to. If you don't, just put one, and a Z stack, so you can choose the top and bottom of your sample. And of course, for all the type of protocols, you can also do a montage. So you can, if this field of view is not enough for you, you can do a 2x2 or a 3x3, or what you need to get a larger area. Other types of protocols are multi-position. So if we do a multi-position protocol, you will see that we also have not only the Z stack over here, but the multi-position settings. So you can take images in different locations of your samples by just adding the coordinates here. And I'll show you later how to do that. You can also do a multi-position without the Z stack. So we will just leave the multi-position settings and remove the Z-scan settings from the protocol. And the finite burst, which is only useful if you're doing very quick imaging with only one channel. So for example, if you're trying to do a DNA paint experiment and try to acquire the blinking of the molecules, or storm, for example. I'm not sure if you have power for storm here. Or if you're trying to do calcium imaging as fast as possible, you want to use finite burst. But it only works with one channel, and it's only just a time lapse as fast as possible for how many time repeats that you put here. So I'm just going to start with a simple Z stack to show you here how it works. So again, time repeat, I'm not going to do any time lapse, so I will do this protocol only once. And I will expand the Z stack settings. So for the Z stack, I'm going to use the piezo. The piezo is just another way of moving in the Z dimension, so up and down, but instead of moving the objective, it's the stage that it's moving. Using the stage to take Z stacks has two advantages. It's faster, and it's more reliable. So if you repeat the Z-stack over and over again, it's going to be more precise than using the objective movement. However, the stage doesn't have a very large range. The thickest Z-stack that you can take using the piezo, if you can see here, I can expand the Z-stack all the way. It's 500 microns. So the scan size, the maximum size that you can scan in Z using the piezo is 500 microns. Now I know that my sample is much thinner than 500 microns, so I'm good with the piezo. If you have something that is thicker than 500 microns and you still need to take a Z-stack, you can turn off the piezo, and that will allow to use or to set your Z-stack using the objective. So when the piezo is off, the Z-stack will use the objective to move up and down and collect a Z-stack. Yes, 500 microns is 0.5 millimeter. Yeah. Okay, so the current position is given by the orange arrow over here. And to set the Z-stack, I can do two things. I like to click on the orange arrow here and use the mouse wheel to scroll up and down. And with this, I am moving the piezo. So I'm moving the piezo up and down. You see the current position is changing here. So I can go all the way down. I'm scrolling down with the mouse and set the start. And then I can click again on the orange arrow, scroll up until I find the end of my sample on the other side, and set the end. And you can see the size, the scan size is 16 microns, so it's a very thin sample. Another way to move the piezo is to use the knob that it's on the ASI controller. So for that, you can just, it's the stage controller. So where you can do the X and Y movement, there is a knob that allows you to move the piezo.
It's a wheel on the right.
Yeah, it's a wheel on the right, right below the display. And with that, it's the same thing as using the orange arrow from the software.
It's safe, you wouldn't break the objective.
You can still. Well, okay. Yes, it's probably the movement is so low that you're not gonna risk to crash. But it's always good to keep an eye on the sample. A good way to tell if you're touching the cover slip and you might damage the objective and the sample is that if you see that you're changing focus but the image is not changing, and instead of maybe changing focus it's shifting left and right, it means that you actually have lifted your sample and the sample is moving and you're not changing the focus because you're already touching the sample. Okay, so I have selected my Z-stack and I know that the size is 16 microns, and now we can choose how many steps we're going to take, or more precisely, what's going to be our step size. So by clicking auto step size, the software will automatically select the Nyquist, so the correct sampling for this particular objective and wavelengths, so that your resolution is good in Z. So in this case, the auto step size is telling me that the step should be 0.18 microns, so 180 nanometers. And we're collecting 89 steps per color. If we look here, we can choose how is the Z-stack being collected. So we can say, if you want to go fast, for each channel, we acquire all Z points. So this means that for the 488, we will acquire 89 steps, and then we move to 561, acquire all the steps, 637, and so on. However, if you have something that it's moving and you want to keep track of all the three colors at the same time, you can choose to take all the colors for each Z position. So in this case, we will do green, yellow, red, move up one position, green, yellow, red. This, however, is much slower because the filter wheel takes time to change. If you're doing some live imaging, not in this case. So in this case, I will do the fast one. And since I know that my sample is quite bright, in order to go faster and save time in the training, I will drop the exposure time a little bit to say 50 milliseconds for all my channels. This is also good enough. I can do 20. Okay. So that's the Z-scan settings. Another thing that we can do, say that I want to collect an area that is larger than this, I can do a montage. So I expand the montage tab and I select it. And I can say, for example, I want to take a 2x2 or a 2x3, right, in this case. And this area where I'm currently right now, I want this to be the center of my 2x3. So the software will collect an image starting from the top left, going down and creating an area of 2x3 around this center. Or you can have different options to where to start the stitching. If you don't know exactly how many fields it will take to cover your area of interest, we have another way to do the montage or the tiling, which is to use the edges. If I select edges, I can remove old settings here. You can give to the software coordinates and it will automatically create a grid to contain all those coordinates and do a Z-stack, a montage inside those coordinates. So for example, I can use the stage, the XY stage, to move around and find the edges of the area of interest. Let's say, I'm not going to do it too big, but say that I want to start here and then up until the other side. Okay, let's say that it's here. And then I will do a little bit down. And you can see the grid size that the software automatically created is a 4x3. And it's based on these 3 coordinates that I gave it. You can put as many coordinates as you want. If you have something that is round, you can just go around the edge and add as many coordinates as you want to make sure that everything will be included. And you can check here your grid size. Okay, once you're happy, in this case I have my Z-stack which is set, the montage that it's set, and I can also say in the image processing option that I want my image to be stitched automatically at the end. So if I turn this on at the end, once we have collected all the 12 tiles, the software will automatically stitch them and I will acquire. Okay, since I've turned on the stitching, the software is asking me what channel I want to use to do the stitching algorithm. So I know that I usually like to select my best signal, my best channel, and in this case is the 561. So I will select that because it has higher contrast and it would really help the stitching algorithm to find the right edges and give me a nice stitching at the end. So now you see we are acquiring different Z position for each channel, and we will move to collect 12 positions.